All right, hello to whoever is watching this, and the purpose of this video is to give a quick update on my progress so far on my master's thesis topic, predicting recessions with machine learning. So let's jump right in. So in this video, I want to discuss the training data, what variables I used, how I collected them, what my challenges were, and how I addressed them. I want to discuss each of the models that I decided to use individually, talk a little bit about the tuning that I performed on the models, and then talk about the evaluation metrics I collected, and then discuss my preliminary results as well as some possible next steps and a conclusion. So my purpose with the training and testing data was to get a data set which is broadly representative of the US economy, which is primarily service-oriented. And I looked at the existing literature on similar topics to gain insight for some input selection, as well as focusing on indicators that are used by forecasters at the Federal Reserve, and specifically the LEI, or the Leading Economic Indicator Index, which I'm going to discuss a little bit more shortly. However, there were several limitations that needed to be considered that made the data collection very challenging, such as the fact that I need to rely on publicly available data sources, as well as the fact that the data series, which are publicly available, vary widely in their length, and I'm going to discuss those a little bit more as well. So first, I want to dive a little bit more into the LEI index, which is one of the key indicators that the Federal Reserve uses in their own modeling to predict whether the US economy will enter a recession or not. However, this indicator alone, I think, is not sufficient and overweights the manufacturing sector too much, and there's actually a bit of a lively debate going on within the econometric community about whether this indicator is still as reliable as it once was, since it's been predicting a recession basically for the past year, and it's kind of failed to materialize, and many attribute that to the fact that it weights manufacturing so heavily. And additionally, the data that is available for the LEI index was cut off after 2021 by the FRED API, so it only goes back to about 1990 through 2021, which is not suitable for the purposes of this analysis. But looking at a breakdown of the index itself and what the Federal Reserve decided to include in it, we can gain some insights into what kinds of variables and inputs would make sense. So I definitely referred to this for guidance in choosing the variables, which I'm going to discuss next. So I just set my mind on 6 what I would consider reliable econometric indicators, many of them based on some of the LEI components, as well as previous studies on similar topics. So the first one being the monthly log change in the S&P 500, and then, of course, the yield curve or term spread, however you want to refer to it. And it's kind of up for debate about what exactly the yield curve or term spread is. Some use the 10-year Treasury yield minus the 2-year Treasury yield. Some use an average of the 10-year Treasury yield and AAA rated corporate bonds minus the 2-year Treasury yield. Some use the 10-year Treasury yield minus the 1-year Treasury yield. But I settled on the 10-year Treasury yield minus the 3-month T-bill yield because I wanted a kind of strict indicator of the yield curve, so to speak, and I wanted to see how that would affect the model's overall abilities. And then additionally, the real log change in GDP month over month. Then an indicator for consumer sentiment, which is based on survey data collected by the University of Michigan and made publicly available through the FRED API, as well as the log change in consumer spending, as well as the log change in industrial production output, which is another data series offered by the FRED API. And then, of course, as the target variable, I use the NBER, or National Bureau of Economic Research Recession Classification Index, as the target variable, and this is basically a long series going all the way back to the 1800s, which basically just simply classifies whether the US is in a recession in a given month or not. And all the data is on a monthly time scale, and the data was sourced mainly from the FRED API as well as the Yahoo Finance API. So there were a couple indicators that needed to be transformed due to a mismatch in the time scale of the data that was publicly available. So real GDP is an indicator provided by the FRED API, which uses 2017 as the base. However, it's released quarterly, and of course we need monthly data. So I decided to use cubic spline interpolation, or just interpolation with an order of 3, to transform the data from quarterly into monthly. And this is a technique that's used widely in the literature as well. And you can see on this plot right here, the interpolated monthly GDP compared with the quarterly actual GDP, and it seems to line up fairly reliably. And then I had to do a similar thing for the consumer sentiment data, which was reported quarterly up until 1978, and then monthly thereafter. So on the left, you see the interpolated data up until 1978, and then on the right, you see the full plot, including the monthly data after 1978. So it seems to line up well enough. However, the consumer sentiment data is just a raw number without a clear base or max. So that data had to be transformed into a more usable scale that fit more with the other variables that we were using. And so the first step was to then test the data distribution for normality. And you can clearly see by this QQ plot that it's not approximating normality enough to assume that it's normal. And this just affects what kind of transformation can be done on the data. So because we know that the data is not normal, we can use a non-parametric normalization technique. And to do this, I used min-max normalization. And the sklearn Python package offers a plugin that makes this calculation automatically. And so this then has transformed the data into a more usable metric by basically measuring the level in terms of where it is on the distribution of the min and max values. And it scales much better with the other variables. And the consumer spending variable is reported nominally by the Fred API. And to do this, we needed to make this into a more usable number. We needed to first change the raw spending level to the nominal change over the past 12 months. And so what that basically means is that the change in consumer spending for each month is in relation to what that value was 12 months ago. So, and this is the technique which is also used mainly by statisticians looking at the year-over-year change as opposed to just the monthly change. So then we needed to then adjust the nominal change in consumer spending to the real change, and I was able to do that relatively simply using an inflation data set from the Fred API as well. And so there was definitely a trade-off between what independent variables I wanted to use, and which ones I could actually use. So again, one of the limitations that I alluded to was the fact that I needed to rely on publicly available data, and many of the econometric indicators that are used today really don't go back that far. There isn't that much data on them. And of course, machine learning models typically need large amounts of data to be able to generalize very well, and there was also huge variability in the time spans available for certain inputs, sometimes from the same API. And basically, through several iterations of trial and error and adjusting which variables I used, I was able to come up with the final data set, which is a monthly time frame from January of 1960 all the way through October 2023. So about 740 rows of monthly data. And so I just want to note before we move on that I am, for the purposes of this analysis, as of right now, including the COVID recessions in my data set. I'm not excluding those as some of the literature has. So the final step is to then just test the independent variables I chose for multicollinearity, just to make sure I'm not being redundant in my variable selection. So the first thing I did was create a heat map of the collinearity between the different independent variables. And there doesn't really seem to be anything too concerning. We see that the highest level of multicollinearity is about 0.58 between scaled consumer sentiment and the change in consumer spending, which is not surprising. But anything above 0.5 I think is worth looking into a bit further. So I then calculated the variance inflation factor for each of the variables, and it's summarized in this table right here. And so we see that there is no VIF score above 5. So I think that the conclusion from this is that there is no multicollinearity problem with the data set that I have so far. So moving on to the models themselves, I use 6 models in total. One, a classic, so to speak, logit classifier model, a logit regression classifier model, and then a feed-forward neural network with 2 hidden layers that used a sigmoid activation function, then a support vector classifier, a random forest classifier, an extreme gradient boosting classifier, which is just a more lightweight, kind of newer version of a traditional gradient boosting classifier model, then a custom consensus model, which I'm going to dive into more specifically later. Okay, so I just want to dive in a bit on the structure of the various models that I'm using. And the structure for the models are essentially the same for all of them except for the consensus model, which I'll discuss in more detail on the next slide. But essentially, the way that the model functions are set up is it's always an 80-20 split between training and testing of the data. And the scoring metric for the grid search, i.e. the metric which is used to then extract the best model based on the grid search results, is the F1 score. And each model has a unique parameter grid, which is passed in. And the function is performed for 5 different lags. And this is the same for every model, namely 3, 6, 9, 12, and 18-month lags, so a total of 5. And on the right here, you see a diagram of how the model is structured, the model function, I should say, at a very high level. So it takes in the data, the respective lag, the test size, which in our case is 20%, the scoring metric, which is the F1, and then a parameter grid. And essentially what it does is it pre-processes the data for the given lag, adjusts it, then performs the grid search cross-validation and extracts the best model, then uses a helper function to find the best threshold to use for the model, again, based on the F1 score. And then another helper function to create the receiver operating curve plot, as well as another helper function to perform and export the SHAP analysis results. And then lastly, an object of various metrics for the given model at the given lag is created and exported, including the model itself. So I just want to quickly touch on this consensus model that I built, which uses a majority voting system for classification. So as I alluded to on the previous slide, every model, once it's done running, is also exported. And what the consensus model does is it imports all the models for each lag. Then each of those pre-trained models are then used to make predictions, and then the algorithm basically goes through and checks how many models voted, so to speak, for a recession at that given point in time. And then if 3 or more models assign a recession, then the consensus model also votes for a recession, so to speak. And the same metrics are also collected for the predicted values. And so this is just another high-level overview of how this model works. So the data, the lag, the test size, That is all the same as with the other ones. And then the summary data is used to extract the given thresholds for the models. So the data is processed, and then a helper function is used to extract each model at the given lag. So for example, the random forest model that was exported at the 3-month lag, and does that for all the models. Then does the exact same thing for the thresholds, i.e. looking at what threshold was identified as the best and used with that model which was exported. Then it takes that from the summary data. Then the predictions are made, and then the helper function is used to check the votes and assign predictions. And then the same objective metrics is then collected and exported. So yeah, I want to touch now on the model tuning that I did, and the main issue that I faced throughout this process was expectedly the large class imbalance, and namely there just haven't been that many recessions when compared to the overall number of months, even though the data set that I have is not that large. And I initially went through and only used grid search and the parameter grids, and this produced very poor initial results, all F1 scores, or for the most part I should say below 0.5, so really no better than guessing. And the main problem was the models kept producing a very large number of false positives. So to help address this, I started manually going through and adjusting the classification threshold from the default of 0.5, sometimes adjusting it up in intervals of about 5% to see how that affected the model's ability to classify. And that improved the results significantly, but still not enough to really be useful. And then I implemented the synthetic minority oversampling technique, or SMOTE, I'm not sure if that's how it's pronounced, using the imbalance learn package. And this is essentially a technique to help address class imbalance, and it uses a sort of like a k-nearest neighbors-esque algorithm to create synthetic data, which can then be used to help train the models, not for testing, of course. And after implementing SMOTE, my results improved dramatically. And in some cases, for example, with the logit model, the metrics almost doubled across the board. So after having made these adjustments, my results improved dramatically. And as I alluded to, of course, the adjustment of the classification threshold is done automatically with a helper function and an algorithm that I developed that finds the optimal threshold on its own. So that's no longer done manually, of course. So then I want to touch on the evaluation metrics that I used. So of course, as I said before, or alluded to, I should say, each model was optimized for the F1 score, providing a good balance between the precision and the recall of the model. And of course, you have to look at the circumstances. Working with a highly imbalanced data set using a metric like accuracy doesn't really make much sense. And then so after extracting the best model based on the F1 scores, I then collected the precision, the recall, the F1 itself on the testing data, and then the receiver operating characteristic under the curve score as well, in addition to the plot that is created for each lag as well. So now the exciting part, I can dive a bit into the preliminary results. So the first thing I did was just basically rank the models simply across each lag and each metric. So looking at each lag and then sorting the models based on their respective scores for each of those lags. So looking at lag 3, which model had the best F1, which model had the best precision, which model had the best recall, etc. And you can kind of see just visually from looking at this table that the models seem to be pretty scattered throughout the different lags, and some models seem to be performing better at shorter lags, while some seem to be performing better at the more far out lags. But it's really clear just kind of looking at this that you can't really draw any concrete conclusions about which model seems to be performing best just on the simple ranking alone. So the next step was then to test for statistically significant differences between the models. And I just want to note that the first test I performed was the Friedman test, and that is because the underlying training and testing data is not normally distributed, and the metric data is such a small sample size spread across so many different models that it's safe to assume that the data is not normally distributed or not even close to that. So all of the metrics that I used for evaluation of the tests are non-parametric tests that don't rely on the assumption of normality. So the first test I performed was the Friedman test, which looks at all of the models and tests if there's any statistically significant differences. And the initial p-value returned by the Friedman test was around 0.0002, so very low. But of course, the Friedman test doesn't tell you which models are different from each other. So then I did some more post-hoc analysis using the Nemenyi test for pairwise comparison. And you can see a heat map of the p-values right here on the right in this figure. And interestingly, the Friedman test has a super low p-value, but then looking at the pairwise comparisons based on the p-values of the Nemenyi test, there don't seem to be any model combinations that are significantly different. So definitely calls for some further investigation. So of course, as I said, relying on the results of one test is not enough. And the next step is to then look at the general performance of each model using some different tests. So I then use a similar approach for pairwise comparison using the Mann-Whitney-U and the Wilcoxon-signed rank tests to test for significant differences between the various model pairs. And this first round looked at all the metrics across all lags, like the Friedman tested, and the Nemenyi post-hoc test. And 4 significant results were identified, though the results from the Mann-Whitney and the Wilcoxon-signed rank tests sometimes conflicted with each other, i.e. the Wilcox-Signed rank test would have a p-value below 0.05, whereas the Mann-Whitney test would have one above 0.05, and vice versa. But of course, the main takeaway is that the logit model was not dominated by any of the models based on these tests, and it was actually the support vector classifier model which was found to be significantly worse than the consensus, the random forest, the neural network, and the extreme gradient boosting models. So then I thought to myself, after looking at the general performance of the models when compared with each other, okay, maybe that's one thing, but then what about looking at it at each lag interval? Maybe there's certain pairs that are significant at distinct lags. And so I basically performed the exact same test using the Mann-Whitney and Wilcox-Signed rank tests for all the metrics for each model at each lag. So not all the models across all the lags. And there was no combination of models which was identified as being significantly different at any lag. So backing up the findings of the Nemenyi tests while contradicting the findings of the Friedman test and the tests looking at the model metrics across all of the lags overall. So still some more investigation which needs to be done. So then I thought to myself, okay, we've been looking at all of the metrics, but obviously the most important one for these kinds of classification models is the F1 score itself. So then I did some further pairwise comparison looking at all of the lags, and using the F1 score. And again, the same thing, the same result was returned as the last round of tests, that there was no significant performance difference between any of the machine learning models between each other, and also between the machine learning models and the logit regression model. So then I did one final test comparing the average scores for all the machine learning models across lags with those of the logit model, i.e. looking at the average F1 score for all the machine learning models at lag 3, lag 6, etc., and then comparing those values with the logit model, using again the Mann-Whitney and Wilcox-Signed rank test. And again, as with the previous test, no significant differences were found. So I think so far the evidence is failing to show that there's any significant difference in performance between the machine learning models, both individually and as an aggregate, when compared to the logit models, based on the scoring metrics I collected and the training and testing data I used, which I think are all valid econometric indicators. And so before I move on, I want to jump into the SHAP analysis, which is, of course, a way of looking at the feature importance identified by the various machine learning models. And one thing I thought was super interesting was how it reinforced the relevance of the yield curve as a leading predictor. And it seems that the larger the lag, i.e. the further out in time, the more weight the model assigns to the yield curve as a predicting variable. However, at the 3-month lag, the change in consumer spending is actually the most important feature across all models. But by the 9-month lag, every model identifies the yield curve as the most important feature. And I just have a little example here highlighting the B-swarm and summary plots of the random forest classifier model at the 3-month and 9-month lags. So we see that at the 3-month lag, the change in consumer spending is the most important input, but by the 9-month lag, the yield curve is the most important input by far. So I look forward to diving into those results a bit more as well. So then quickly moving on to some next steps, I'm going to continue writing the literature review as I have been, and I think that should be finished relatively shortly. And I'd like to request a code review, especially for the code that's performing the evaluations and making the statistical comparisons. And I'd also like another meeting to address some questions I have about the structure of the thesis, especially the methodology section. So then just to bring it all together, the initial results seem to indicate no significant performance differences between logit and machine learning models for recession classification. And I collected the training data using several econometric indicators that try to represent the US economy as a whole. The class imbalance was the main challenge that I faced with my training testing data, and I addressed this by manipulating the decision thresholds, performing grid search cross-validation, and smoke rebalancing on the training data. And each of the models were evaluated on lags of 3, 6, 9, 12, and 18 months. And the F1, ROC, area under curve, precision, and recall scores were all collected and tested for statistically significant differences. All right, thank you for watching, and I look forward to discussing these topics further.